All right, we're going to talk about the definite integral, and that's what we're going to be spending the rest of the week on, and then tomorrow and the next day we'll actually get into what the definite integral is. But today we're going to start with kind of leading into what the definite integral is by estimating what are called finite sums. So go ahead and write that down. We're going to estimate finite sums. And the way I explain this is I want you to think about when we did particle motion. Okay, think back to when we did particle motion problems. And probably a problem that you ran into when you were in 8th grade was something along these lines. You got a train moving along the track. Singing Casey Jones. Never mind. So you got a train moves along the track going 75 miles per hour. And it leaves at 12 o'clock noon and arrives at 3 o'clock. How far did it travel? Most of you, it wouldn't take too much to figure out the answer to that problem. If you know it's traveling at a constant speed of 75 miles per hour, and in 8th grade you didn't consider direction, so when you talked about speed, you just assumed it was traveling the same direction all the time. So you said 75 miles per hour, going down the track for 3 hours, how would you calculate the distance traveled? 75 times 3, which would be 225 miles. Pretty easy problem. It was just distance equals rate times time. What I want to show you is that it is very much related to what we're doing in calculus. Let's consider the same example as a calculus problem. Let's say that we know the velocity, function. Remember, position, velocity, acceleration. Velocity is the what? First derivative of position. So we have 75, and we'll put this in miles per hour. Let's say that we have the same problem that you ran into probably in 8th grade. And let's say that it traveled, the train travels from noon to 3 o'clock p.m. Okay? So how long does it travel, or what is the interval of time that it traveled? But how are we going to label that on an axis? Because we're not going to label it with time. We're not going to put 12 o'clock on the x-axis and 3 on the x-axis. So what do we typically do?
1, 2, 3 hours.
Yeah, we'll just go, we'll put the starting time will be what? 0. Anytime we decide what the start's going to be, we all need to understand something about a start. It doesn't necessarily mean it's 0. Start is all relative to what you're talking about. Okay, for example, if we talk about Hunter's age, Hunter's age is going to be based on the year that he was born in, even though that's not year 0. That's not the beginning of time. Okay, so I'm assuming I'm going to guess 1995. Good call. Year I graduated. So for him, that was the year I graduated. That's the year I started college. For him, that's the year he's born. So my starting 0 for college is year 0. His starting year for birth is 1995, which is 0 for both of us, but it means something totally different. For me, my age, my year 0 is 1976. Okay? For you guys, when you get married one day, you measure your marriage, how many years you've been married from the date that you were married. That's your year 0. Okay? So when we label this, we're not going to put 12 to 3 on the x-axis. What are we going to do? We're going to put from 0 to 3. So this would be the interval from 0 to 3. What we're doing is we're setting 12 o'clock to be the start. You're saying 12 o'clock is the start. That's the point of reference, just like when you build a house. Okay? And you start paying off that loan. You start, the moment you borrow that money to pay for that house is the moment you start paying it back. So you measure your house from when it was built and when you start paying back the house and paying off that loan or mortgage or whatever it is. Okay? So you kind of get the idea. And that can be with anything. So that point of reference in time, you get to set the start. And what's really cool about calculus, you can set the start a lot of times to whatever you want it to be. Okay? So, if I look at this example, and if I was actually to graph it, so let's think about this. Let's say that we have this here, and let's go ahead and put 75 way up here. Here's 75, and we know velocity is on the x-axis, and that is just a horizontal line. Everybody agree? Okay, 75 is just a horizontal line. So my velocity graph is just a horizontal line. If I only measure from 0 to 3, so there's 1, 2, 3. Take a look at this. What shape do we form?
Rectangle.
Now rectangle. I want to show you something interesting about that rectangle. What is the height of that rectangle? The height of that rectangle is 75, and it is in miles per hour. What is the width of that rectangle?
3.
So from 0 to 3, it'd be 3. You guys just told me a minute ago to calculate the distance traveled, it'd be just 75 times 3. What is that also related to here?
The area.
It's related to the area underneath the velocity curve. So what we are getting into today, and what we're going to be starting, is area underneath the curve. Now I want you to notice, it was measured under the curve to the what?
X-axis.
So it was the area under the curve measured to the x-axis from 0 to 3. Okay? So if the width of the interval, let me measure this, this is 1, 2, 3. So the width is 3. And the reason the units, now, I want to show you, everything agrees here. So this right here ends up being 225, and here's why. And it's in miles, because when you take velocity, watch this, velocity times the interval, which would be the change in time. This is going to get interesting here tomorrow. If you take velocity times the difference in time, or the time interval, the length of that time interval, here velocity is measured in miles per what? Hour. I'm going to come back to this in a minute. Delta t, or the change in t, is just what? 3 hours. Hours. What happens to the hours? Cancel out, and you end up with miles. Now what I want you to see here, this right here represents the height of the rectangle. That was the height of the rectangle. This was the what? Width. Don't lose track of this, because that's coming back here soon. Okay, we will get back into that, because tomorrow I'm going to tell you that this is going to become your integrand. This is going to become your dx, and you'll see where the definite interval plays into this. Okay. All right, so basic idea is that, guys, the area under the curve calculates what we were trying to do in 8th grade. It calculates total distance. Now, we're going to give the proper terminology for it, because it actually is not total distance. It's actually displacement. This calculates the displacement. Now, the reason we didn't care about displacement in 8th grade is because we were only traveling one direction. You didn't care about the direction. In fact, in the problem, it never said anything about the direction. It just says the train's traveling 75 miles per hour for 3 hours. How far did it travel? You didn't even consider direction. But now that we're past 9th grade, 8th grade, and 10th grade, and 11th grade, we do consider direction. In Calc 1, we only consider rectilinear motion, which means we only consider motion in a straight line. So we only get to go what? Right or left, that's it. You don't get to do multivariable. You don't get to do multiple directions. You only get to go right or left, or you can do motion in a straight line up and down, and you can go what? That's vertical motion, up or down. That's it. That's all we get to do in Calc 1. If you take Calc 2 and Calc 3, then you'll start to combine those directions into vectors. And if you've taken physics, then you can start talking about the horizontal component and the vertical component that'll actually, you know, if you're traveling an airplane and you've got a wind pushing the airplane, what's your course actually going to be? Okay? Or if you decide, if I want to travel to that point in the room, I'm not just going to go straight and then turn right. Maybe I just want to walk straight to that, and it's a resultant vector of your horizontal component and your vertical component. So you get into multivariable stuff. But we are limited to just left and right or up and down in this class. So you don't have to think about that. Somebody already said, well, what happens if you go this way? We're only going one way. We're going right or left. Okay, on these problems. So that brings up the next example I want to look at. Let's say, okay, that's easy to do. You can do that with geometry. In fact, all of you can do that if it was a horizontal line. But here's the thing that we know about the math that we do. Our velocity curves are not always going to be straight. Let's say that's the train now.
Should we be writing this down?
Sure. There's our train. And I want to know the distance that it travels from some point in time to start. We'll just call that 0. We don't know what it is. It could be 12 o'clock, it could be 3 o'clock, it could be 4 o'clock, whatever. And I want to know the distance traveled from 0 to whatever. I don't know, 10 hours. Let's just say 10 hours. It could be anything. 0 to 10. It's still going to be the area under the curve. I hope I just convinced you just by looking at the rectangle. But the problem is, if I've just convinced you that distance equals rate times time calculates the same thing as the area under the curve does, how are you going to calculate the area under a curve that you don't have a geometry formula for? That's where calculus comes in. Now, what we are going to do today is you're going to just estimate the area. And the way that we estimate the area is we simply do what we just did in the last problem. We use rectangles. And here's what I'm going to do. I'm going to take and say, all right, I know that there is an exact area under the curve, but I don't know how to find it yet. So what I'm going to do is I'm going to start, and I'm going to look at both endpoints, and I'm going to decide which endpoint I want to use. The left endpoint or the right endpoint. I'm going to let you guys pick it. Left, okay, fine. I'll use the left. So if I use the left endpoint, I'm going to start right here. I'm going to measure the height of my rectangle to the curve. And then I'm going to finish my rectangle. Now, when you look at the area under that rectangle, will it approximate the area under the curve? Will it be exact? Probably not. It would be extremely, you'd be the luckiest person on earth if you hit it exact. Okay? You're not going to hit it exact. All right? The area under this rectangle, the area under this red curve, the velocity graph, can be estimated using rectangles. And so if I find the area of this one rectangle, it'll give me an approximate area for that area under the curve. But I don't want to just approximate. And I don't want any approximation. I want my approximation to be good. So how can I make the approximation better? Nope. How can I make the approximation? Use more rectangles. Well, if I can do it with one rectangle, it's just like when you were in 9th or 10th grade or 8th grade and you were in middle school, I don't care, 5th grade, and you had something that looked like this. You remember doing these problems where you were asked to find the area of it?
Yeah.
What'd you do?
Found the area.
You divided it up into what? Found the area of that rectangle, that rectangle, that rectangle, that rectangle, and then what'd you do? Add them all up. That's exactly what we're going to do. We're going to find the area of multiple rectangles. So if one rectangle is good, two must be better. Actually, not always. It actually takes a little while before it starts to really get better. But one's good, two might be better. Once you get further down the line, they keep getting better and better. But at the beginning, they might not. Because you might look at one and say, that's pretty good. Let me ask you this, because on the AP exam, they'll do this. They might ask you, does it over-approximate or under-approximate? This one actually probably looks like a little bit over. Okay, because there's more area here than there is here, so it probably over-approximates just a little bit. Now, they'll make it really obvious. You'll never have to be like, I don't know, it looks close. It'll be clearly obvious that it over or under-approximates, and they will ask that question. They will ask you, does the rectangles that you use to estimate the area of the curve, does it over or under-approximate? And there's 4 ways that you can estimate area of the curve, and I'm going to teach you all 4 today. 3 are with rectangles, and 1 is with a trapezoid. Okay? So here we go. Let's show you what 2 would look like. Do you want to go with left endpoint again? So the way you do is you take your interval from 0 to 10 and you'd split it into 2 rectangles. How would you split it then? Where would the split occur? At 5. So the first rectangle would be from 0 to 5. You following this? So then you would do the left endpoint. You'd start at 0. That's your left endpoint. You would measure the height to the curve, to the velocity graph, and then you draw over until you get to 5. There's 1 rectangle. Let me put it in actually blue or something so you can see it better. So this is 1 of your rectangles. So the next rectangle from 5 to 10, what would the left endpoint be? 5. So now you measure, watch this, start at your left endpoint, you measure up to the velocity curve, then you go over to 10. And there's the next rectangle. There's 2 rectangles. What do you think? Better approximate than 1? Maybe a little bit, not much. I don't think there's a lot of value in 2 rectangles versus 1. It really starts to be much better the further you go with this. How about 3 rectangles? I'll use green this time. How about 3 rectangles? I'll show you how to partition it later. There's a trick to partitioning it. It's just your length of your interval divided by b minus a. It's real simple. It's a real simple formula. I can show you partitioning later. All right, 2.5. What about halfway between 5 and 10? 7.5. You ready? Here we go. Green. Let's do left endpoints again, just because that's what we went with. So 0 to 2.5 would be the first rectangle. So you go from 0, you go up to the velocity graph, you go over and down to 2.5. And then what's the next from 2.5 to 5? What's the left endpoint? 2.5 to 5. What's the left endpoint? 2.5. Go up. 5 to 7.5. What's the left endpoint? 5. 7.5 to 10. What's the left endpoint? And there you have 4 rectangles. And some of the rectangles over approximate and some of them under. So look at the first rectangle. The first green one under approximates. The next green one looks like it's maybe a little bit over. The third one a little bit. The fourth one, maybe, man, it's not, I'm sure it's not right on, but barely over or under. Wouldn't even matter on that one too much. So then you'd probably argue that it over approximates more than it under approximates. I don't know. My graph's not drawn very well, but at least you get the idea of how to start this. This is called estimating with finite sums because you're finding areas of multiple rectangles and then you just add them up. Finite sums. Why do we call it finite? Because we're going to know the number of rectangles. Sums because we're just going to add up the area of all those rectangles. When we estimate using rectangles, it has a special name. You ready? Estimating using rectangles. Using rectangles is called Riemann sums.
What? Where'd that name come from?
The guy that discovered it.
What a selfish dude. Named it after
Pretty much all mathematicians are that way. That's why my trinomial factoring method is called the Morse method. Okay, estimating using rectangles is called the Riemann sum. Anytime on the AP exam they ask you to estimate using rectangles, you're finding a Riemann sum. Now, they might just say, find the Riemann sum using a right endpoint. And you have to know, if they say, find the Riemann sum using a right endpoint, you just know Riemann means what? Riemann means what? Rectangles. That's all it means. The only time they won't say Riemann is when they want something other than rectangles, and then they're going to tell you exactly what they want. And the only other way you do it is if you don't do it with rectangles, you're going to do it with trapezoids. And they won't say Riemann sum in that situation. They'll say use trapezoids.
There's no name for the trapezoid.
Nope, it's called trapezoidal rule or use trapezoids. Okay? Alright, yeah.
Yeah, you could call it that.
Yeah, I suppose. Not that good. Alright, so estimating using rectangles. Let me show you what this looks like. I've got a better graph because I can't do justice to this because I am not artful at all. So let me stop the video so the videos are not so long to watch in one shot. So,